Over the course of the last unit, we spent really a lot of time talking about transferring energy using work and power, etc. But we haven't really talked about storing energy. Now, a lot of times when people think storing energy, they think batteries or something else like that, something electrical. But really, most energy is stored in one of two kinds, either potential energy or kinetic energy. And now these words sound really scary, but they are really very simple concepts. Kinetic energy means energy to things that are in motion. That's what kinetic means. So objects that are traveling fast have kinetic energy. Potential means it's all stored up, and this often means gravitational. The most common example of which is stuff that's way in the air. For instance, water on the top of the mountain, water in a lake at the top of the mountain, or an object that's been lifted up into outer space. So for this lecture, we're going to go over kinetic energy. And the first thing we notice about kinetic energy is it depends both on how big the object is and how fast it's thrown. Obviously, the amount of energy you feel, the amount of energy it takes to get moving, a ping pong ball, is way less than the amount of energy it takes to move or the amount of energy you receive from a thrown bowling ball. And that's because the bowling ball has way bigger mass, and as a result has way bigger energy. So we know that somehow the kinetic energy, and we'll write Ke for short there, is going to depend on mass. But what else do we know? We also know how fast it's going matters also. After all, a bullet might be really, really small, but it has the power to shatter through wood because it's going really fast. By contrast, a giant lump of stone sitting on the ground, it may have huge mass, but if it's not moving, we can't really say it has any energy. So we're going to also say kinetic energy depends on velocity. Now let's look at how it depends, because that's going to be very important. Let's make a graph of kinetic energy and mass. As we look at this graph, and we do some experiments and graph some points, we'll see that this is a line. And this means that kinetic energy equals some constant times mass. And that it's assuming that everything else stays the same. The velocity stays the same, etc. And now let's do this again for the velocity. Once again we have kinetic energy, but this time we're graphing with respect to velocity. But this time it's not a line. This time it's a curve. The more velocity you have, the faster the kinetic energy increases. And that's actually quadratic. That means the velocity is squared. So the kinetic energy is going to equal some constant, we'll call it d, times the velocity, but squared this time. So now let's combine it together. Since we're keeping velocity constant in the case of the mass, we can replace velocity with a constant there. So kinetic energy equals v squared times m. And the same goes in the other case. If we're holding mass constant in the second example, we can replace the constant d with mass. So kinetic energy equals v squared times m, and that looks tempting, but we're not quite done. We're still off by one constant. That entire thing needs to be divided by 2. Now it might seem a little crazy. Why does it matter to divide by 2 if we're defining our own units? But this is where it gets really special. As long as we use SI units, which in this case are going to be the second, the meter, and the kilogram, we get our answer out in joules. And that's very, very useful because we'll have it in the same units we have for work and power, etc. So in this case, the standard form of this is kinetic energy equals 1/2 mv squared. And what this means is that we take an example. For instance, someone takes a 2 kilogram weight and throws it at 10 meters per second. What does that mean? Well, that's 1/2 times 2 kilograms times 10 meters per second squared. And we write that out. 10 squared is 100 times 2 divided by 2. That equals 100. And like I said, the answer is in joules. So we can calculate the energy contained in a thrown object using this very simple formula. So next lecture, we'll go over a similar formula for potential energy, stuff that's lifted up in the air. And pretty soon, you'll be ready to combine these two and learn about the conservation of energy.